Okay, we're going to look at adding and subtracting vectors with a simple displacement problem. If we read it carefully, it says a turtle crawls 8.7 meters east, then turns and walks another 5 meters north, rests for a little while, turns and walks 3.5 meters east and another 3.5 meters south. What is his final displacement? So clearly we're going to have to arrange this question with vector notation and see what happens in the end. Let's start by drawing each vector as we see it. Now remember, vectors are represented by arrows. The length of the arrow represents the magnitude or the number. So in other words, the 8.7 meter vector will be longer than the 3.5 meter vector. And the arrowhead should point in the direction given. So let's start with our 8.7 meter vector that pointed east. Now you don't necessarily have to take a ruler out and get exactly to scale 8.7 meters, but as long as you make a reasonable commitment, if that red vector represents 8.7 meters, then we know the next vector, when he turns 5 meters north, has to be shorter, not quite half, a little more than half. So let's now draw in our 5 meter vector north. Now this is an addition question. The turtle is walking 8.7 meters east, then 5 meters north, then 3.5 meters east, and then 3.5 meters south. And when you add vectors together, you add them together tip to tail. We've got 8.7 meters right here. There's the tip of the first vector, and we're adding to it a 5 meter vector. So the tail of the 5 meter vector should touch the tip of the first one. So let's rearrange that now. So there's our first two displacement vectors added together. Now let's read it again. He rests for a short while and turns and walks another 3.5 meters east. Let's put that one in now. Again, tip to tail. So we're now ending at the 5 meter vector and walking another 3.5 meters east. Lastly, our turtle turns and walks another 3.5 meters south and ends up at the location provided on the screen. Now remember what displacement is asking. It wants to know what his final position is in relation to where he started. It becomes a vector. Okay, so our final displacement vector must start where the turtle starts and end, of course, where the turtle ends. And it'll look like our blue vector that's drawn on the page. And the goal is we want to find the length of this vector and also the direction at which it's pointed. It looks like it's pointed a little bit to the north of the east line. So we're trying to figure out what that small little angle is in the end. Now, it becomes a matter of simplification. Just like adding and subtracting regular numbers, you can add and subtract vectors in any order you like. So what we want to do is cancel things off. Let's deal with the horizontals and the verticals separately and see if we can simplify our drawing. Let's rearrange our diagram, starting with the horizontals added tip to tail and then the verticals added tip to tail, and see if it actually equals the same answer. I'm going to move our resultant vector, the blue arrow, and we're going to rearrange our diagram so that we first add the two horizontal vectors, the 8.7 meter red vector to the 3.5 meter red vector, and then we're going to add the two green vectors, the 5 meter vector and the 3.5 meter vector. Most of you are probably way ahead of me now in recognizing where this is going, but let's have a look at how it actually looks in the end. Okay, so I've separated the vectors. The vertical are off to the right and the horizontal are on the left. Let's add the two horizontals together tip to tail. So 8.7 plus 3.5, you can see that we get a much longer vector pointed to the right. What is the magnitude of that vector? Well, all we're going to do is add the 3.5 to our 8.7. And when we do that, we'll get 12.2. So we've simplified it. We've collapsed the horizontals down into one single vector that's 12.2 meters in length. Now let's have a look at our two vertical vectors. If I travel 5 meters north and then change direction and travel 3.5 meters south, obviously I'm going to end up a little less in the northerly direction. and we're going to have to subtract these two vectors. So let's have a look at how that looks by first putting them together tip to tail. So if I take my 3.5 meter vector and I place it at the tip of the 5 meter vector, we notice it ends up right where my hand is, right at that point right there. So my resultant vector in that case is 5 minus 3.5. And it'll still be pointed towards the north because there's a bigger northerly component than there is a southerly component. Let's separate it just a little bit so we can see what's going on. So our overall vertical component is simply going to be 5 minus 3.5 meters, which is 1.5 meters to the north. So you can see our 1.5 meter vector at the bottom. Let's get rid of all the clutter and get our simplified final vector down. So what we've done is simplified this problem down to 2 vectors only. Basically, all of this statement can be collapsed into saying the turtle walked 12.2 meters in total to the east and 1.5 meters in total to the north. So when we draw our tip to tail diagram, it'll look a little bit different but yield the same results. So let's place these vectors tip to tail and see what it looks like. We can see that the blue vector is the hypotenuse. So we want to solve for the hypotenuse of a right triangle, and all we have to do is simply use Pythagoras. Tan theta is opposite over adjacent, and in this case opposite to the angle is our 1.5 meters and adjacent to our angle is 12.2 meters. So we end up getting tan theta, which is 0.123. To find the angle, we go second function tan, or tan inverse of 0.123. And I end up getting an angle of 7 degrees. My overall displacement is 12.3 meters, rounding off the 12.29, at 7 degrees, and it's swinging to the north of the east line. So north of east. There's my final answer. So all we're trying to do is take our vectors and simplify them down into 2 vectors. Now I chose some strange numbers here for a reason. This question that we took quite a while to solve is identical to the following question. A turtle crawls 10 meters in a direction 30 degrees north of east, then turns and crawls 5 meters towards the southeast. What is his final displacement? Believe it or not, these 2 questions are identical. They'll yield the same final answer of 12.3 meters at 7 degrees north of east. Let's see why. If we grab a 10 meter vector that's headed in a direction of 30 degrees north of east, it will look like this. And we're going to add to it 5 meters at an angle southeast. Now in physics, southeast, northeast, northwest, that automatically means 45 degrees. So you that's just something you have to know. So our last vector will look like this, and we're going to add it tip to tail once again, and there's my vector diagram. Now this actually gives us the same results as our other question. It gives us the same answer. There you go. Gives you the same resultant answer. Now, again, you noticed I picked some strange numbers on the original question. 8.7 meters east, then 5 meters north, and then 3.5 meters east and 3.5 meters south. Let's look at our second version of the same question, and we'll see where those 8.7 and 5 meters come from. So let's separate our 10 meter and our 5 meter vector. Okay, so here's our actual question. We've got a 10 meter vector and we're going to add to it this 5 meter vector pointed downwards at 45 degrees. Now what we want to do is break the 10 meter vector up into vertical and horizontal components. We want to do this because we saw how easy it was to deal with things that were all either vertical or either horizontal. We can easily simplify the picture. So all we want to do is change this 10 meter vector into a horizontal and a vertical component. To do that, we simply make a right triangle out of this 10 meter vector. The horizontal part will be the x component and the vertical part will be the y component. Let's see what that looks like. We can use sine or cosine to figure out what the green and the red is since we know the hypotenuse. So if I want to find the red side, I would simply go 10 cos 30. And then when I do that, I end up getting 8.7 meters. Similarly, if we look at our green vertical component, I would simply go 10 sine 30 and get 5 meters as my vertical side. So our 8.7 meter and our 5 meter sides are known as the components of this 10 meter vector. So notice what we've done. We've taken a vector that's at a funny angle, 30 degrees, and we've simplified it by saying if I walk 8.7 meters east and 5 meters north, I achieve the same results. So I've rewritten my 10 meter vector as horizontal and vertical. We could even remove it if we like and finish the question from there. But let's leave it in for now. If we do the same thing with our 5 meter vector and figure out what the two components are of this, we get the following. So now that we have the components, it's pretty simple. We can add our x's together, or our horizontal components, to figure out what my overall horizontal vector is. And we can look at our two vertical components to figure out what we get overall vertically, just like we did before. So horizontally, I get 8.7 plus 3.5 to get 12.2 as we had before. Vertically, 5 meters is positive. 3.5 would be negative because it's down. And when I add 5 meters plus negative 3.5, I get positive 1.5 meters just like before. So it's a way of simplifying our question down to two vectors only, a horizontal one and a vertical one. And then finishing the question is exactly like we did before. A little bit of Pythagoras to get our hypotenuse, our blue vector, which ends up being 12.3, and tan theta to get the angle. And again, we'll get 7 degrees north of east. So that's what we're trying to achieve with the component method. The main thing is when you do components is to make sure you watch the direction of the components. It's vitally important. So anything that's up, we'll say is positive. Anything that's to the right is positive. Anything that's down will be negative. And anything that's to the left will also be negative. So add up the x's, add up the y's to get my overall x and overall y.